recording there. Okay. And so first, wanted to talk a little bit about homework 4 and also remind everybody next week is the week we won't have normal classes. So there's no scheduled synchronous lectures, whether they be in person or remote. You know, we'll be all participating via Discord as necessary over the course of time. So just think of it as more, if you have an issue, bring it up on Discord. I'll try to get to it in as timely a fashion as possible. But there's basically, you want to use it as sort of studio time to work on, kind of get some of the homework 4 stuff done leading into your project, right? So you can use next week also as a lot of sort of project-based time. Now, I guess, let's see, I had it first open here that we had, let me open up under content. Let's look at the syllabus just to remind us where we are. It's always challenging to figure out, especially during the summer, you know, are we halfway through the semester yet? So to me, it always feels like 2 weeks in, I always feel like, oh my God, half the semester has gone by, and have we covered everything? And, you know, so we've been sort of front-loading, which is good. I think the pace, to me, feels kind of reasonable, and we're a little bit even ahead of what we have on here. In terms of, if we look, what's today? We're in that, is today the 14th, is that right? No, today's the 17th. Today is Thursday. Wow, okay. Now I'm getting even crazier. So we're at 17, lighting and materials, which we more or less talked about last time. So we're good, we're ahead. Now, next week normally would be shadow mapping, percentage PCF, percentage close filtering, cube map, sky domes, environment mapping. But we're going to kind of flip this studio up to Monday and Thursday of next week. So it'll be more studio time. And shadow mapping, PCF, cube map, sky domes, environment mapping, and so on are not part of our midterm project or project 1 anyway. So we're in good shape on that. And we'll talk about that, you know, when we get back and sort of introduce the topics. And they are also, of course, available on Learn OpenGL. So it's accessible, it's out there, but it's not part of, the big news is not part of Project 1. So we don't have to necessarily worry about that. We're going to swap Studio in there. We're in actually pretty good shape. And even though it feels like we're halfway through the semester, we're not really even halfway through the semester. So, or the arch, whatever you want to call it. So I keep reminding myself we're in good shape. I think we're in good shape. So the first thing I wanted to discuss a little bit, and I'll post this as part of the normal presentation slides, but it's not quite part of the normal presentation. But let's talk about homework 4. I don't know, I think a few people have already kind of jumped into homework 4. Most people are still kind of finishing up homework 3. That's fine. Homework 4 is the first kind of big one in terms of sort of implementing code more on your own, you know, looking at the way that the shaders are done on Learn OpenGL and the way that they were done in the last lecture, really looking at, you know, some of the math behind, you know, the way that light hits the model, how you have to figure out, use that to scale the lighting, and so on. All right, now most of it is there, and if you look at, you know, refer to the lecture, I don't know if the lecture videos will definitely be available tonight, both today and Monday if it wasn't already up. I'm losing track of that too. But the one bit that wasn't in, that I didn't show in the slides, if you pause on the shaders, was that we didn't include the specular. We talked about it, and it's certainly covered in the Learn OpenGL, but that's one part you'll probably have to, you know, kind of dig a little bit deeper in, kind of in terms of doing it on your own. Now, there is, however, realizing this, that there's sort of a hidden task in homework 4. One of the reasons to have a little bit more time to do it, and one of the reasons that'll be helpful in terms of project 1, in that when you're doing lighting, when you're working with lighting, obviously, hopefully obviously, you need to have normals to do it effectively, right? Your model needs to needs to have normals so that you can figure out those incident angles, how light is hitting the surface, the angle of the normal compared to the eye, and so on. And in the sandbox, really haven't implemented anything with normals in the sandbox. In discussing spheres and toruses and even the OBJ model loader, for example, we did talk about how normals, we can load them or generate them from there. So it's sort of a hidden task in Homework 4 that you have to come up with some sort of way to have a model that's going to have normals, right? If you want to do something really, really simple, I think Learn OpenGL, they basically, in their tutorial about lighting, they have another cube that has a set of normals set up for it. So you can kind of do that as well. I'm going to start with that one, or advance more into reading an OBJ file or doing something procedural, because we want to see that in Project 1 anyway, right? So a little extra time on Homework 4 because you're going to use a lot of that stuff, hopefully, in your midterm project, right? So a word on normals. Someone had asked on Discord, I don't know if it was in the general chat or just a one-on-one, about like, well, in the case of models, or in the case of generated procedural, I have a sphere, for example, sphere being the easiest case, how do I get the normals for something like that? What's the easiest way to do that? So I mentioned, and I think I mentioned this last time, that the sphere is a nice case specifically, and you can do this for certain types of models, where if you know the center of the model, and you know any of the vertices, or you know each of the vertices in the model, like the case of a sphere, all you have to do to get the normal is basically subtract the point or the position of the vertex from the center of the model, right? We wind up with a tangent plane, we wind up with a normal, it's just basically a vector that points out from the center. If you normalize it, you say, okay, it's not positional, it's just a direction, boom, it just works, right? So a sphere is a really, really, really nice case of that, because all of the points on the sphere are equally spaced around the center. So the question becomes, well, what about other types of models, like in the case of the torus or case of cubes and so on? Then it gets fancier, gets more interesting, because, of course, the surface is not necessarily, or the tangent to the surface is not necessarily perpendicular to the center of the model. So, for example, in the case of a torus, you have to look at sort of the slice that contains all of the vertices you're interested in, and then they center in sort of the center that sweeps around the torus, right? Not the center of the torus, which is sort of just in open space inside the middle of the donut, right? So you'd follow, if it was a jelly donut, but not the kind of jelly donut that's just totally filled. Imagine a jelly donut or a stuffed crust pizza, right? More of a thing. Trying to come up with a good analogy, where the stuffing in Little Caesar's stuffed crust pizza goes around, so you'd have to go to the center of the stuffing in that, or wherever the jelly would be in the jelly donut that actually had jelly that was all the way around the donut. Weird way of talking about it, right? But imagine in this case, the simple one, where if I took this as a circle and swept it around to create that torus, this would be the center, and I could calculate the normal for each vertex on that particular slice, and then sweep by whatever number of degrees I want to get my next set of vertices, and so on and so on. I think we're hearing some noise from somebody on Discord, because it's a bit of a rumbling on the speakers here in class. Okay, no problem. So I wasn't sure if it was like background noise or imposing about thunderstorm about to hit or anything like that. No problem. So, wanted to bring up this. This shows up a bunch of times, and it's easy to sort of not notice, but you should certainly be aware of it, because when we talk about how OpenGL interpolates a lot of the values that it has, for instance, even the texture coordinates, or potentially even interpolating the normals, or interpolating any of the positions, and so on. How does it do that? How does it actually interpolate points on the a primitive, like a triangle? And typically, it uses something called barycentric coordinates. So it's basically, it is interpolating the values according to their, when they are potentially lying on different lines, or how close they are to the vertices of the triangle that encloses them. So one of the interesting things about this, if we think of these in terms of normals, for example, and I have an image on the board here. Well, this is where the real world and the virtual world clash a little bit. So imagine that this lower right one here is one of the two triangles forming the face of a square, the face of a cube, right? Our cube, each face is made up of two right triangles, and you can see that along the diagonal of that triangle, which would be basically the center of the face, we wind up with half of this coordinate and half of this coordinate, whatever attributes belong to that vertex, contributing to where we would be at the center here, right? So if we think about a cube and we did our same trick, where we said, okay, let's draw out through each of the vertices. If we share the vertices in a cube, we only use 8 of them instead of trying to over specify and have 24 vertices. If every face, every vertex had a unique one, there'd be 24. No, sorry. Yeah, 4 times 6. Yeah. So in this case, if we drew out those vertices, and here's our really crude drawing on the blackboard here, you can imagine them kind of pointing out at diagonals at all the corners. And if I did this weighting here, the weighting of this point would wind up, sure enough, being halfway in between these two and kind of pointing straight out again. So it almost feels like, well, maybe the interpolator will come up with the right value for a flat shaded square, cube even, right? Because if you just look at the interpolated value at that point, at the center of the face, it would come up with probably the right thing. So maybe we could just calculate the normals for a cube using what's built in. And the problem is we really can't, because that would require us to say, well, okay, forget about the fact that it's interpolating along all the other points in there, right? It's correct at the center, but it still would come up with these kind of interesting kind of shadings, right? So we can't really do that. However, it does give us some intuition. If you did want to calculate them, potentially there are ways to do that. And as we get into things, crazier sorts of geometry shaders and so on, maybe you could do that if you had a really, really complex model where you want to do it and then feed it back and then store it. Don't calculate them always on the fly, but it's sort of a cautionary tale here in terms of like, yes, sometimes the hardware is there to do it, but you have, in order to get the hardware to do what you want it to do, you wind up jumping through all sorts of hoops in order to get there. And sometimes it's just better to calculate it ahead of time, or you'll find a lot of the time when people talk about doing textured cubes or lit cubes, you just bite the bullet and you say, okay, there's 24 vertices, and you have your own colors for each of them, you have your own texture coordinates for each one of them, and so on, right? So sometimes it's best to not kind of overthink or undersimplify, in this case, trying to approach the cube in the same way as a sphere, right? And do be aware of these, barycentric coordinates. Again, we're not going to have to calculate any of them ourselves, but it's basically how OpenGL, how the hardware is figuring out which texture coordinate, which, how to interpolate the normals, and so on. It's doing a mix of each of them according to a line in between the established vertices, and then taking interpolating, and so on and so on, right? So be aware of barycentric coordinates. So now a bit more about Project 1. A basic scene. That's the idea, to have a basic scene in Project 1. You know, we talked about some of the ones that show up in computer graphics kind of all the time. But sometimes I have to remind myself that this is not a CS course. It's not a computer science course. What do I mean by that? Why do I bring that up? Well, being within HASS, being humanities, arts, and social sciences, and on the gaming side, I say, well, all right, we should be thinking about the kind of creative use of these technologies. You know, what do we do with them? You know, how do we apply them in artistic ways at least? We have to choose one of the letters in HASS to kind of align ourselves with, so we have some justification for being here. But it also allows us a bit to have some leeway in terms of what we do, and we're not doing just exactly this, and it's got to be critically perfect, and so on and so on. So it's a lot like programming in games to begin with. It's about the experience, it's about the end result, and so on. So what does that mean? Well, it doesn't. Someone might say, well, you know, this is a New Yorker cartoon where, you know, someone talked about computer graphics or computer art. Is it just the application of, you know, technology to do the same sort of thing? So it's just, you know, another medium. And certainly we're not going to go for that. We're not going for necessarily photorealism, exactly what the real world is, that sort of thing. You know, so if you want to have elements of that, so be it. But I'm not asking you to go high art. Don't worry, we're not into that realm either. However, I do like the notion of saying, well, let's go for something more abstract or even surreal, right? So we're not going to study art. We're not going to get into surrealism and abstract expressionism and all that sort of thing, unless, you know, you want to do a little bit research on your side. That's totally fine as well. But let's think about ways, instead of just cubes and just flat surfaces and, you know, okay, it's going to be this model, this model, this model, and the Utah teapot in the middle. You know, yeah, creating a program that does that is as simple as cutting and pasting, right? Bending the rules as we get in there and say, well, what happens as we start using affine transformations? Or how do objects relate to one another? Or what is there in the scene? This is an image by Salvatore Dali, famous painter in the early 20th century, early mid-20th century. Worked with Walt Disney at one point. They started working together on potentially doing it was going to be a 10-minute short. It never wound up kind of coming to fruition. There's just, I think, 10 seconds worth of video from it, or 10 seconds worth of film content created from it. Dali is really famous for, you know, the melting clocks, you know, that sort of thing, all sorts of very, very abstract images and warped perspectives and lots of, you know, very, very imaginary terrains and sorts of things. So I think that's kind of a good jumping off point to think about, well, what do we want to have in our scene? Could it be, you know, just completely the mundane, bunch of different objects? Sure, but try to think about, you know, manipulating them in some interesting way, or applying them in some different way, or creating some sort of landscape, something to your scene that makes it unique. What can it be? Could be anything. You know, sometimes wide open is even harder to do that, or to figure out, but we'll leave it pretty wide open. So, a scene artfully demonstrating, here's the techniques, some sort of generated model, which can be, you know, cubes, spheres, torus, platonic solids. They're all the kind of even-spaced side solids. You know, you typically think of them, I always think of them as the Dungeons and Dragons dice, right? Everything up from four-sided up to 20, right? Those are the platonic solids, and there's lots of information out on the interwebs and so on about, you know, how to create those geometries. Another piece, some sort of externally generated model. Maybe it's Suzanne, the monkey from Blender, or the teapot, or the shuttle, or something beyond that, right? You could either use some sort of DIY parser, like the OBJ parser we talked about in class, or there's, you know, great resources about that. I'm happy to kind of go into a little bit more about that today as well. Or potentially using the asset importer library, which is way more advanced and potentially has, you know, is more complex to implement, but there are some good examples of it, including at Learn OpenGL. You want to have some use of textures. It can be loaded and or generated. We generated our own texture using our line drawing techniques if you want to get fancier like that, or you want to manipulate them, or want to do different things. That's a possibility, but we have definitely some use of textures in your model. ADS lighting, of course, mentioned that as part of important part of homework 4. You want to have at least one light source if you want to get fancy and experiment and try, well, what happens when you have multiple light sources? We're not going to get into shadows just yet. We're keeping that for the future, but potentially you could say, well, how would I implement multiple light sources if you wanted to? And some form of animation. And by animation, I don't mean anything too complex, right? It can be accomplished by a number of different methods. We're not talking about deforming anything other than as a rigid body. You could use affine transformations, which aren't technically rigid transformations because they will cause a certain amount of shape changing. That's pretty trivial use here, but we're not talking about jointed or skeletal animations or skinned animations, anything like that. Just real simple, right? And even the sandbox that you have so far is using some primitive animation. All it's doing is over the course of time, it's incrementing a number and using that to kind of slide an object around. So that would be the most basic form of animation. You could potentially do that. You could make motion interpolated or absolute. Like so far, things have been absolute. We'll talk a little bit about interpolated motion today. And last but not least, this can be sort of linked to animation a bit, but also talking about interactivity a bit, and it's also kind of covered in a little bit in the sandbox about using IM-GUI or some other sort of interactivity, right? Because this isn't just still images we're talking about, since we're graphics for games and so on. We want to have that sort of live feel to it, interactive feel to it, right? Doesn't have to be, we're not developing a game engine or anything as elaborate as that. We're talking about simple motions, use the techniques we've covered in class and in that basic Learn OpenGL piece plus basic lighting. All right. So one of the biggest challenges you'll probably encounter during the project is going to be the architecture that you sort of adopt into, how do you get things to work together, right? You kind of think of it as a bit of an engine. If you have multiple objects, how are you going to organize that? What kind of data structures will you create? Will there be something that has, okay, here's a VAO that belongs to this particular object, and here's a set of keyframes that belong to that object, and here's a set of positions that belong to that object that you want to move through, and so on. Right? So thinking about what are the objects in your scenes? How independent are they? Do you have to run through a list of different objects in the scenes and render them, and so on and so on? How are you going to approach that? Right? Be organized. No need to get carried away. You're not really, you don't have to invent a game engine. You might decide, do you want to use multiple VAOs, vertex attribute objects, which is probably true if you're using multiple materials, like if you have solid cubes versus a textured object or something like that. VAO is probably one of the simplest ways to kind of have lots of distinct objects. That's the way I've been doing it in the sandbox. Or you could use some of the clever VBO techniques that we discussed. So if you have things that have some sort of common shading, or they're just using basic lit properties or things like that, you could get away with having lots of things in one VBO and just load lots of objects into that same VAO and just shove all your attributes into a single VBO or set of VBOs. And lastly, this notion is if you are animating, or how you're animating, or how you choose to do animating, you might want to have something like a sequencer, something that determines what changes when, what type of events might happen in your animation, in your program. When do textures get swapped out? When does materials change? If you wanted to implement something that was, say, a glow in a shader that changed over the course of time, how would you control that? Would it just be simply, okay, every time time ticks, I increment a value until I hit a certain point, or or are you smoothly ramping between different things, or having events. Right? I'll talk today a little bit about a simple sequencer. Right? And again, what does that core game object look like, and how does it work with our sequencer, or how do we animate it and make it do stuff? All right, so that's a little bit more background on the project. We'll see how it goes. And again, I'm expecting things to be interesting. It's not going to be cookie cutter, and that gives you lots of room and lots, leeway in terms of what things you can do. Right? Not going to be overly critical on content, but just see how you're doing things in a basically good way, and using good technique in a creative way. Okay. So let me back up now, back into kind of what I want to talk about. So real quickly, let's talk about IMGUI for a bit. And I don't have a lot of slides on IMGUI because it's sort of meant to just be something that is simple to adapt. And there's a couple of videos I'll point out. One which is mine, I created a couple of semesters ago, and a few other ones that just kind of go through the basics of setting up IMGUI. I know some of you might be using IMGUI on other platforms other than Windows, and you're probably going to have to refer back to the sort of the source on here. So if you go to github.com /IMGUI, that is the home of IMGUI. Lots of great information on there, what versions you need, and so on and so forth. And in the sandbox, there is actually a very elaborate IMGUI demo lurking beneath the surface. This is actually provided in all the IMGUI. If you download IMGUI and you get the library, this is kind of sneaks in there, this show demo window. So if you modify the code, you look for this part in the sandbox, and you add this line, show demo window, you'll wind up seeing a demo window that will include sort of all of the capabilities of IMGUI in all sorts of different ways. It's not going to really interact with our program much, but it'll show you all of the different things that IMGUI can do. So there's some good IMGUI tutorials, and my video on including IMGUI into an existing project. So those are there for resource sake. Now, what does IMGUI mean? Why do we call it IMGUI? What is it? Let me go ahead, and if my computer survived, let's see, I guess I do need to reopen this. Had a crash this morning, and get back to the sandbox. So some of you may have noticed, and to figure this out, this is mentioned in homework 3, that when you actually build your project, things wind up in this build folder, right? We had of course, our solution file in here, but the end result that's built is here in the debug folder, and that includes our executable for our program, as well as a copy of the data folder that you might have, anything in there which includes your matrices, your shaders that you save, and so on. Double check the explanation in homework 3 where it tells if you want to shut off the overwriting of those. Make sure everybody's seen that. Important to have. But this is where things kind of wind up. So if you want to put a model into your game, or change the texture, or directly manipulate some of these things, you may need to go into here. I'll kind of explain why that might be useful in a second. So let's go ahead and open up our solution and talk about IMGUI a little bit more. So the IM in IMGUI stands for immediate mode. Now, it doesn't mean we're using immediate mode of OpenGL necessarily. All right, let's try to recover that then, if that is an issue. It means the way that you interact with the IMGUI library is sort of as if it was immediate mode, right? You're constantly saying, you either say, okay, draw this control on the screen, and then the moment it's drawn and you interact with it somehow, the next time it's just gone again, right? It only exists kind of for that moment for purposes of saying, okay, did something get clicked on? Did I get a value returned back and so on? But they really live for a very, very, very limited window of time. So any of these things in IMGUI, all of our, draw a button, for example, every time I ask IMGUI, I just say, okay, draw this button, and I check the response back again. Right? So it's actually drawing it, and at that moment it checks, are you clicking on that? Is that saying, true, yes, that button was interacted with? Right? So it only exists, there's no button state that lives after that. So I draw it, I check its value, I do something based on its value. Similar to everything else that goes on here, if I say, okay, use shaders, it will tell me at this particular moment, did someone click on it? If so, do what's necessary. Right? So it's always just at that moment of time, we draw it, we potentially have an interaction with it. It tells us, here's the value that came back literally at that moment. Right? You'll never see us referring to data that might have belonged to the IMGUI library. I don't set up like, oh, here's an array that you're going to write stuff to, and later on I read it. It's really just like at that moment in time, here's a buffer, here's the type of interface you're going to draw around it, and I get results back immediately, right? Immediate mode GUI, or immediate GUI. So in our simple case, I had set up the certain objects like 4 floating points. This is a set of 16 floating point numbers, 4 at a time, with labels 1, 2, 3, and 4. So if we see the, hopefully this will draw, like that, those 4 float 4s, here's one line, here's the next line, here's the next line, here's the next line, and that is this set of 4 lines right here. Right? If I deleted any one of them, that line would then disappear. Right? So it's positioned, drawn, everything about it is taken care of at that moment. The one thing, sort of, kind of, a little bit of a violation of that there is some state that the library maintains that we don't know about, which is basically, you'll notice I didn't say where these should be drawn. Right? Because IMGUI does sort of keep track as you add things to the screen in between setting up this frame and drawing stuff, it will kind of keep adding stuff below it, kind of adding stuff into that frame, right? So I'll have a line that's this, and then the next line, then the next line, then the next line. Or I could force it and say, oh, okay, here's something, don't draw another line instead, just be on the same line, but at this position. So there's a little bit of state that it maintains about where to draw the next item. It's the one bit of it that's a little bit different. So in our draw IMGUI that's in the sandbox, there's really just a begin to draw the window, simple text at this moment in time, draw this text, and then things like, show this text that is the shader and potentially get input back from it, which is just the current state of it. Right? So at any moment, this vtext is going to be what's drawn on the screen and also what we are using live for that vertex shader. Right? So we have our 2 shaders being drawn. Then we have our simple set of buttons. So the use buttons, a use shader button, and then it says, okay, on the same line, the save shader button, and then on that same line, the swap texture button. And then after that, those matrices, or the rows in the matrix, say, and then end. And then it tells it, okay, go ahead and basically draw whatever's there and throw it all away again. Right. Now, in what I had on the screen now, I had to do it. I had to get a little Lego minifig in there. That was a model that I loaded into Blender and exported as an OBJ file. So as you're looking to do that, I'll show you, give you some hints on how to get them to behave. If you're not careful, you definitely can generate OBJ files that are more or less complicated. I'll give you some hints on that in just a second. But you'll notice, in addition to our standard window over here, there's also this window that I'm drawing up here, which is the IMGUI demo window, and it'll show all sorts of great stuff. Text boxes, configuration stuff, widgets that you can use, everything from bulleted items, bulleted lists, list boxes, combo boxes, images, range widgets. So if you want to set between a range of 0 and 98, because that's the upper end of the range, I guess. Yeah, now that'll move. What do we got here? Slider flags. I don't know what that one is. I haven't seen that one. Drag and drop vertical sliders. Kind of cool stuff. So imagine if you wanted to move an object around and you had an X, Y, and Z rotation, an X, Y, Z position, and so on. Color pickers. These are fun as well. If you want to pick a color, a typical color picker like you'd have in Photoshop or Unity or wherever. So you could change the color that the object was being drawn with, or change the color of a light source, or kind of on and on with that. And additionally, I think you can also get information about the mouse, current position and things, whether it's being dragged, and so on and so on. It's surprisingly complete, surprisingly capable. It actually shows up in a lot of programs you might not know. There's a full list of things. I think the Godot editor uses IMGUI as well, but it's amazingly powerful, and it's great to just kind of start off with just a little bit. One of the trickiest things is kind of setting up in the first place, and the trick to that is just knowing which files you need to have. Normally, like in GLFW, there's a version that we need because of that. If we were using glue, we'd use a version according to that, and so on and so on. But if you're just using and building your project similar to how the sandbox works and similar to how Learn OpenGL works, you can continue to use the version that's included with the sandbox easy enough. Right? So one of the things I wanted to mention, the reason I mentioned the folder that I could go in and actually change these things in debug, data, for example. When I loaded in this model, this particular model, and let's see, I don't have Blender open. Let me go ahead and I'll open up Blender. So if you're interested in editing models or doing things or even converting models back and forth, Blender is a great resource to have. I just accidentally opened up 2 copies of it. Yeah. No reason for that. All right. So I had a Blender file, blend file. That was just a Lego minifigure. And by default, one of the things that I noticed right away that I'm interested in getting rid of, it turns out this model also has a floor here, this big flat area, which I don't want, so I chose that and just deleted that. You could get as elaborate as you want. If you find it's a good challenge to find a full-on scene. There's no reason that you could have a town or a house or anything inside Blender and export it as an OBJ file. See how that goes. I'll just start with a simple one here. And said File, Export, and since we're interested in OBJ files, since they're the easiest to use or the easiest to parse, I chose OBJ file. And to kind of simplify the file format just a little bit, you'll see there's export options over here, and everything is more or less okay, except the geometry. By default, this might not be the case. Yeah, it's not the case, so we'll have to reset it here. So you can see which things will be included. So apply modifiers is fine. It's going to apply anything within Blender to create the model. That might be subdividing surfaces or smoothing edges and all that, and that's all totally fine. We want to write the normals. We definitely want those. We want to potentially include UVs if it's a textured model. Write materials. Whether or not we use materials, it's going to depend. At this point, I'm going to say keep your exported objects from Blender pretty simple. Maybe you don't bother writing materials because we're not going to try to read them. We're just going to say, okay, one texture per object or one texture per model. You can leave this selected or not. But the important thing is to say triangulate faces. This simplifies the model to make sure that all faces are triangles. Otherwise, Blender will allow for n-gons, right? You can have triangles, quads, or whatever, even kind of odd shapes like that. We don't want to do that. So this is one of the key things to make sure that your typical simple OBJ parser is okay with that. Right? So triangulate faces and say export. And it will create that file. I don't know where we wind up putting it. Let's see. Let's see. Whoop, I don't want to do that. Did I send it to, okay, Blender. Well, I'm going to look at the version that I exported earlier today, which I put into ironman.obj. And this doesn't include a floor. It's just our little Iron Man minifigure. And I can right-click on it. And I'm going to open it with Notepad. The nice thing about the OBJ format, we can actually do that, and see kind of what's involved here, how complex it is. And quickly notice that, let's scroll to the bottom. The file itself consists of roughly, well, 35,000 lines. So there's a lot. It's a non-trivial model. There's some nice curves and smooth surfaces in there. So it's a lot more complex than you might think. And it actually does contain, I think, multiple meshes in here. The head it actually has a head inside the helmet, and that's a different material. So it's like a flesh tone Tony Stark head as opposed to the red of everything else. But the important things are to notice that, sure enough, there are V, which means vertex positions. And once we scroll down through a few tens of thousands of those, we'll see that we have texture coordinates, UV coordinates, basically. And later on, we'll have vertex normals, and ultimately faces. And the face has the position, UV, and normal indices. Right? So to parse a OBJ file, the trick is to read in all this information first. Read in a list of vertices, or a list of positions, a list of UV coordinates, a list of normals, and then use the faces, this combination of these three, to create an attribute for each vertex, combining those three things into an actual set of attributes for a vertex. Now, my other side point was to look, if we look at these numbers here, just the coordinates here, you'll see that these numbers, let's see, x, y, and z, see y is 15, 20, 17, fairly large compared to if we look at the coordinates that we're using for the models inside of the sandbox and perhaps even in OpenGL, Learn OpenGL. So there's no rules about, like, you can have a model as big or whatever the baseline size is. So if you're not careful and you just go ahead and depending on, now I'll go in here and I'll sort of break this for myself. Let me create a copy of this. All right, and I'm going to set this matrix to just a set of default values, right? So this will be 1, 0, 0, whoops. Too many zeros. 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. All right, so that's my default matrix. And I'm just going to go here and run this version of the sandbox. And you'll notice immediately what happens is I just have this really big, in this case, I guess it wasn't so bad because the first time I loaded it, it included that floor, and the floor completely obliterated everything on the screen. I couldn't see anything. You can get into situations where you just can't see any, because the model is always in the front of IMGUI. So if you ever open this up after trying to load a model and you can't see anything on your screen, it might be because your model is just too big. And the way around that, of course, would be to set this to some smaller value, 0.01, 0.01, 0.01, nice little minifig. But if you can't get to this, it's kind of tough to do. So your other alternative, of course, is to actually go into this file and edit it, and hand change your coordinates here. So sometimes to get yourself out of a jam if you've got some model that just shows up too big, and you want to set up a new default matrix for it, that's something you can do. Something to be aware of. Okay. So this is the I've generated a kind of a rotation matrix for it, so you can kind of see it at an angle there, and it is lit using just the ambient and diffuse parts. And you'll notice you can't see it too well on the projector, but actually the lighting is changing, and this is sort of a bug on my part. I'll just point this out for you to figure out a better way to do it in your project, is as part of the lighting, we transform the normals, right? Because the normals have to change in addition to the vertices changing. If just the vertices change, then the model will move around. Let's do that. Let's say now, matrix 3. All right. So now the model is moving around, and if you want to refer back to this, you'll see that there's also a piece in the vertex shader where the normals are being transformed by the inverse model matrix times the, in this case, the moving model matrix, and that's to get all the surface normals to move around and be scaled accordingly. You can wind up, if we don't if we don't transform the model, but we do transform the normals, you'll get kind of lighting effects, which are a little bit weird because your normals are all kind of moving around the surfaces in odd ways. But it's important to get both of those to make sense, and that works out better. So be aware in your ADS lighting to transform both your normals and your vertices, positions, to get your lighting to work correctly. All right. All right, back here again. So in our code, the type of animation that's currently going on is all just based on, simple increments of time. Right? If I look at the uniform matrix that I'm sending, in that case it was matrix 3 was the spinning one here. Right? Here's how I'm generating that uniform matrix, right? So I'm passing it to my shader using GL program uniform matrix 4FV, and I'm passing it into that location that it knows about, and the value that's being put is transform 3 there. And transform 3 is created up here, where I start off with just a identity matrix. I translate it a little bit, so it's kind of moved a little bit on the screen. And then I animate the rotation by rotating that transform in, so I'm using the kind of unit YZ direction, and the angle is, I'm just passing in the time, right? So I'm just continuously, every frame, saying, okay, this amount of time has passed, so this number of degrees, this number of radians, the rotation happens about that angle, right? So at a steady rate, that rotation occurs. This would be sort of like the simplest kind of animation you could do. Just something changes over the course of time. We have a simple way of mathematically doing it. If we wanted to do something fancier, maybe we said times 1.5. Slightly fancier, and that would make us animate at 50% faster, right? I'm going to get back again. I didn't save my shader. So, where did I break something? Yep. And he's too big. So let's go back in here. And I want to use this. Get rid of that one. Use my normal one. And I can even go in here and edit my shader. I could, let's see, go in here and that. I suppose even at this point I could just run it right from there. So it's rotating that much faster, right? So the animation is really just controlled parametrically by my parameter. Whatever I decide to do. But I can't get particularly fancy, and it's constant, it's continuous, it's always moving that same way. So what if I don't want it to move always in that same way? What if I want to have non-trivial animation, right? So non-trivial animation, where it's just not time incrementing some value or sliding it across the screen, it's going to be using a combination of, or potential combination of a bunch of different techniques. Things like mixing or lerping, slurping, linear interpolation, spherical linear interpolation, and sequencing. Now, hopefully you're all vaguely familiar, at least, with interpolation, right? Interpolation is a type of estimation, a method of constructing new data points within the range of discrete set of known data points, right? Point A, point B, we interpolate between the two, you're going to move from one to the other, right? It doesn't have to be just a location, it could be between colors. Might we be careful about that? RGB colors don't necessarily blend all that nicely. But for things like, if you want to change the intensity, or you want something that starts off very dull and just becomes more and more red, that's easier to do as opposed to going between mixed colors. But you can interpolate between all sorts of things, right? Euler rotations, colors, those don't necessarily blend particularly well. Quaternions, which are orientation, they do blend, but we have to use some specific functions to actually do that if we want to get fancy, right? So ultimately, interpolation is about changing blend weights of two values or some number of values over the course of time, right? You start off with 0 of one thing and 1 of the other, eventually wind up with 1 of one thing and 0 of the other, right? Imagine it, you have simple idea of having some kind of mix knob that you turn from progressively from one end to the other, go from 0 to 1, right? You have just a knob that you can control. If you turn the knob at constant speed, at constant speed, then you are basically using a linear interpolation, right? As a constant speed. There's no reason you have to do it at a constant speed. There are all sorts of ways to use easing in and easing out and different sorts of exponential functions to kind of create smooth up and down. But for now, lerping is enough. And here's a good example using GLM, right? Since that's going to be our new favorite math library. And this example is about interpolating between two transformations. So there's some extra steps. You'll notice we pass in the two transformation matrices, matrix 1, matrix 2, and this float time. And by time, it's actually between 0 and 1, 1 being the end of the increment, 0 being the beginning of the increment. So you're always moving between 0 and 1. That's our notion of time. It's not time in seconds or hours or minutes, anything like that. It's just some beginning and end, 0 to 1. So to do it smoothly, the first thing we do is we actually decompose those matrices into their quaternions. So we pull the rotation bit out of it, right? We create rotation 0 and rotation 1, and we use spherical interpolation, slurping, to interpolate between those two rotations. Right? So that gives us a nice smooth change in orientation or rotation. And then we can use simple mixing to come up with a position interpolation, right? And this is just going to interpolate between the two matrices, but we have to be careful about what portions of that position we kind of use up. You'll see here we wind up with a vec3, right? So we wind up with a translation here, and then we combine the two back in again. We say, all right, the final matrix, we turn our quaternion, our interpolated quaternion, back into a normal matrix 4 transformation, and we set the position piece of it, which happens to be final matrix 3, that row, according to our position, right? So we fill in the rotation portion of the matrix using our cast quaternion, and then we fill in the translation component, or that one particular row, using our interpolated position. So it's a two-part process, and in the end we pass that back, and now we have a way to do that. So right, if you need to interpolate a position and a rotation over the course of some time, here's a rotate with translate, rotate and translate function to do it. Great for reference, right? In case you want to build your own version of GLM that makes sure to have all the support for that, or for other types as well, where we want to do actual axis angle and interpolation between things that way, you can add additional features to GLM by including different parts. By default, things were already set up for you in the, I believe they're already set up for you in the sandbox though, right? All right, so now we know how to handle rotation and translation properly. Decompose transformations into quaternions, do spherical linear interpolation between the quaternions, and then do a straight linear interpolation between positions, and then combine the two back into a transformation. So, what do we do? How do we get there? How do we start at one and end at another? When do we change? So on. So we might want to use some sort of sequencing or animating or keyframing technique to do that, right? When you want to move between a set of points, this might be something you want to use. Now, if we look at a game engine like Unity, let's set right here. Let's look at the animator, or the animation window, or the sequencer, whatever you want to call it, inside Unity. I think that's the right one. Excuse me for just a second, I just want to. Before I get overcome with the humidity of my mask here again. Generally, it's nice to have a GUI tool to do animating in, right? It's tougher to do it just straight up code. But at least if we can kind of conceptualize it, looking at an existing tool, it'll hopefully make a little bit more sense as we talk about, you know, the programming or the player behind kind of the authoring piece. So hopefully some of you are familiar with the Unity engine. We have a scene in here, a game window. It's one of the classic apple picker programs, right? There's a thing that moves along the top of the screen here and it drops apples down. And did I save the animations? I think I did here. Oh, didn't include that. All right, well, for our purposes, we'll really just be looking at the window here. So in a tool like Unity, is everybody who isn't familiar at all, who's never used Unity? Never used Unity, or? Okay. In that case, I'll fill in just a little bit. So the idea is, you know, in terms of animating, by default, Unity likes to use a keyframe animation technique, and we're going to be doing something sort of similar, or talking about something similar, where at certain points in time, there's a value you set. So in this case, I'm looking at the animation window in Unity. There's a position that's set to be -8 to 0, x, y, z. That's at time 0. And then at some point later on, 1 second later to be precise, the x position has changed to 4.33 or 4. We'll call it 4.34. And then roughly a second later, it has gone back to negative 8.1. So it started off roughly 8, moved to roughly 4, or sorry, roughly negative 8 to roughly 4, and then back again. All right, so we set certain positions in time. Each one of these events had some time for them to occur on. And we had a value. See our little diamonds here specify, yes, this is a keyframe. This is the value at that keyframe. And as I'm moving in between here, you see the x position changing, but there's no keyframe. There's no actual information. The way it gets that information is just interpolates in between these two. So if I look at this curve, for example, it'll tell me, okay, here are the control points. Remember our Bezier curves, right? This is a cousin of that, where I can set control points to control, okay, how is it going to interpolate from point to point, right? I'm going to create that curve on the fly. And in the simplest case, where we might have, just set to, say, both tangents are set to linear, right? So if I set the type of tangent for these to linear, it's just a straight linear interpolation. So we'll start off thinking that way, right? So I start at this time, the value is negative 4.37, or sorry, starts off at negative 7. Now I changed it, negative 7.6, all the way up to here linearly, right? So to figure this out, I just need these 2 points, these 2 events. And then over the course of the time, I'll do the interpolation. So in our program, we need to say, well, how do we keep track of those events, and then how do we ultimately make things happen at those times? Right. So what structures could we consider? Maybe lists, queues, arrays, vectors winds up being a particularly good way of doing it. This one, which should I do this in? Did I do this in C#? I guess I did. No. All right. Well, I'm losing track of what languages I'm in. Let's talk about it conceptually. All right. So if I had a list and I want to just push things onto the list, so I have events that I want to go through, start at the top of the list, work my way to the bottom. In this case, we're not going to worry so much about the authoring piece of it, more about the playback piece of it. Right? We're not going to create the whole Unity animation window and so on. It's more about what's happening and how we get to it. So imagine I create a structure that's called my event. And my event, in this case, just has a floating point for the time and some thing that I want to have used as some kind of integer. Maybe it stands for something. Maybe it's an index into a table of pointers, or maybe it's an index of values. An index into a array of structures, perhaps. Right, so you get fancy. Right, so the second part is up to you, or maybe your structure, your event structure, even has some of that stuff kind of built into it. But the important part is you have a time, and then you have some data that you want to have at that time do something. Right? So what we do, ultimately, the simplified version here, is that you'd say, all right, let me push onto my list events at certain times. So you can imagine I push a time 0, event 1, at time 1, event 2, time 2, event 3, and so on and so on. Right? Now you could get fancy and say, well, is that the amount of time to pass in between? Is it an absolute time? Is it wall clock time? To say, okay, once it's 2 seconds, do this. Or is it 2 seconds after the last event do this, right? You have choices, flexibility, and so on. So ultimately then, what has to happen during the course of our play now, once we get into our play loop, we iterate, we set the list back to the beginning so that we can work from the beginning of the list through the end. And we check, in the course of our loop there, we check, okay, is the event that's at the top of the list there, has its time passed? So this is the absolute version. We say, all right, we get time over and over and over again, maybe GLFW get time or what we're going to do. Compare it to the time of that event. And if so, if that time has happened, do it. Like in this case, we just print it out. Right? This is dumb code. All it's doing is saying, okay, my event, print, this is what I'm doing. Then move to the next event in that list. Checking to see, did you hit the end? If you hit the end, well, maybe you circle back to the beginning, or maybe you're done. It's up to you. So if it was just a looping animation, you would say, I got to the end, reset the list, and move on. Right? So you could, for example, in here, maybe your event, you decide there's a certain time, and there's a position and a rotation, and a VAO, some type of vertex array object that defines some mesh somewhere. So you would say, all right, I know the VAO, I know that objects can get rendered all the time, so that's happening outside of this. But at certain points, I need to change my model matrix according to the passage of time, right? So I calculate a new model matrix based on the rotation and position I'm moving in between. Now, this case here it has no idea about interpolation, right? Just, okay, after a certain amount of time has passed, print this. After a certain amount of time, print this, right? It doesn't really know. You're not interpolating between some past state and some current state. You're just saying, this happened, or this needs to happen. So it's sort of an event that occurs. If you want to smooth things out and actually have it not just pop from this location to this location, this orientation pop, instead you want it to interpolate, you need to look at it and say, well, all right, now maybe it's the same thing. We have this value, 1, 2, 3, changing over the course of time. Most things look the same. We can move between these events, get to the next event in our list the same way. But outside of that piece where we say, all right, in between we know that there's some event in the past and some event in the future. Right? This is really just giving us, what those two events are ultimately. We know which one we've passed. We know which is the next one. So here, now we get in a situation where we say, all right, say we want to do something interpolated, we could use our interpolate function and now look at and interpolate our value to say, okay, here's the current time, here's the last time, that's how much time has passed. And here might be, okay, here's the time of the current event and the time of the last event, so I know here's the interval in between those two. Right? It's important to say how much time has passed and what is the interval. And then you interpolate, the further you are into the interval, the closer you are to using that 1, which is you want this number to go from this piece here, ultimately is going from 0 to 1, and then it's going to blend between the last thing and the new thing, using whatever mix method it needs to. Like here, it might just be a simple weighted averaging of the two according to how far along that distance you are, or whatever you need to do. Right? So that's the basic concept of using interpolation in a sequencer like this, or in some kind of play loop like this sort of thing. That basic bit seems like not a heck of a lot of code necessarily, but it is extremely powerful. So let me show an example of something we do in game architecture. Find the right version of this. So this model here is something loaded with the asset importer library that I mentioned before, ASIMP. And it lets us load, a whole model in with textures and so on. It's, hides everything under the covers. This is actually an FBX model, which is more complex than an OBJ model. Animating a character like this is considerably more complicated than just using an OBJ model. You can imagine we're not, even though it looks like it, and in the end it might be, all of the vertices are likely moving. However, you can imagine if we specified a position and tried to animate each individual vertex, that would be really, really complicated, considering that in this model there are there's got to be more than that. 7,600? I thought there's more than that. I have a couple that are even more complicated. So maybe there's 8,000 vertices in here. If I had a different position for every frame of the animation, that would blow up real quick. So in the case of a model like this, where you're animating it, typically what happens is we animate not the vertices, but we animate a skeleton. That is a simplified version of the model that is just a set of bones, and we can kind of rotate and translate each of those bones to an appropriate position. So in this case, there's, I think, 31 bones? Yeah, 31 bones in this model. So we only have to interpolate a position for 31 things over the course of 60 times a second or however fast, which is way, way, way easier than 8,000 of them 60 times a second. But it's the same idea. It's the same sort of thing where we are rotating and translating each of those bones smoothly over the course of time, because in the animation, in the actual FBX file, it specifies, the animation says, okay, here's a position and a rotation as a quaternion and as just a position. And then you interpolate between the two, and you move them over the course of time. So it may seem like a trivial bit of code, but it's exactly the same sort of thing that builds to something like this. We have another, the simplified version. That guy has 23 bones and only 15 or 1,600. What else do we have here? Anyone? I guess that's it. And these are all, lit, using simple lighting. So the techniques build on one another. They definitely build on one another. Any questions on sort of the sequencer and general interpolation? No? All right. In that case, I guess I'm early on today. We're ending up early. Okay, if you want to use the rest of the time here to ask questions about your specific project or about the homework, or want to work on the homework, or wherever you want to go with it, that covers it for the materials, and we're definitely seem to be on track, assuming that everyone's got what they need or feel like they can work from here towards something. Oh, I had a good, so speaking of the weird dolly effect, this is what's sort of fun. Inspiration, one bit of inspiration, if I could find it now. this the one? This is when good animations go bad. Sort of like, that one shouldn't really do the inspiration. Where's glitch dance part? There we go. This is another fun one, kind of the surreal Salvatore Dali thing, where at some point everybody sort of starts melting because there's a limit, some limits clamped on what the transformations could do, and there's some bugs in there. I thought it was just fun to kind of then experiment. Glitch art is a true thing. I don't know how many of you heard of glitch art on. You should definitely check it out and maybe use that as some inspiration for your project if you want to see, what's possible, what happens as you change parameters, what kind of weird things can you do, transforming objects and coming up with things, come up with little stories. That became my glitch dance party video. So pull inspiration from wherever you can, not expecting masterpieces of kind of profound artworks, but some clever creative use of things, and we'll see how that goes. All right, we'll end early today then. I'll see everybody online throughout the week and see you back in person not next week, but the following. So, all right. Enjoy the good weather. Hopefully we'll have, I guess it's going to rain. Is it going to rain later in the week? Maybe a little bit. Everybody online okay?
Yes.
Okay.